Also, the objective that we are covering here are um, understanding the key concept of transformation of functions. So transformations of functions that basically involves the basic transformations such as the translation. So I'm going to cover up first is translation, just a quick review of that. And then we have um, the reflections. So reflections, and then we got stretches. So stretch stretches or dilation basically. And after this we have the inverting functions, but that is something which probably take up in the next fragment. So what we get started with is first is the translation. Now when we are given a function which is, let's say, firstly f of x, for example, is, let's say, any exponential function a to the power x, or let's say if it is any quadratic function like such as x squared plus 2x or something like that. Now what we are asked to do is, like, based on the graphs that we are asked to calculate or, like, to sketch the new graphs, such as for the functions, let's say f of x plus 2, or f of x minus 2, um, or f of x minus 2, let's say f of x plus 2, something like that. So whenever you have these transformations, these are referred as translation. So in this, the object size doesn't change. It's just the movement gets affected, like the position of the object gets affected. So I'm just going to get started with first is translation. So whenever the translation is about whenever the functions have are moving up or down. So first is, let's talk about f of x minus a, f of x plus a. So I'm just going to show through one of the exponential function, which is, let's say I have y equals to 3 to the power x. Now 3 to the power x is an exponential function here, which is got some critical properties that it cuts the y-axis at 1. And here the horizontal asymptote is basically x-axis, which is y equals to 0. So now the first part is, if I show that how it moves, how the addition of some value affects this translation, I mean the movement up or down. So you can just have a look at it. So let's say if I'm adding f of x plus a as a slider. Now when my slider is at 1, basically it is the graph is 3 to the power x plus 1, which means that the graph has actually moved 1 unit up or 1 unit basically down based on the sign. If it is -1, like here, you can see that it is the movement is basically down. And if it is +1, it is going to move up. So logically, my asymptote also, like the graph has earlier was the asymptote was y equals to 0. Now the new asymptote that we got is basically at y equals to 2. So this is basically the vertical translation. So whenever your graph has got f of x plus a, your graph basically moves a units up or a units down based on the sign. So if I have, for example, f of x minus 2, the graph is moving 2 units down. If we got f of x plus 2, the graph moves 2 units up. So when you're asked to sketch the graphs like 3 to the power x minus 7, 3 to the power x, let's say, or 2 to the power x minus 4, straight away you can say that, okay, I have got the graph of 3 to the power x or 2 to the power x, which is like more or less same, and then move 7 units down, and this one moves 4 units down. So what we notice is that this is the new horizontal asymptote, which is y is minus 7. So new horizontal asymptote is y equals to minus 7. And here the new horizontal asymptote is y equals to minus 4. So this is the first part. And now let us talk about what happens is when you're moving the graphs to the left or right, which is horizontal translation. So when the function is of the form f of x minus a or f of x plus a, in this case, the graph moves actually a units down, a units to the right, and this case the graph moves a units to the left, a units to left. So let's just have a quick look at the example now. Uh, for example, here let's say I'm going to take f of x minus a slider. This is my, let's say, f of x graph, which is f of x is, let's say, 3 to the power x graph, and I'm going to take a slider f of x minus a. So f of x minus a, what actually it does is it's going to move the graph to the left or right based on the value of a. So you can see that when I play the slider, you can see the graph is moving to the right, it moves to the left. So depending upon the value of a, your graph nature is determined. So now, for example, at an instance where I have graph of f of x minus 9.75. So I'm going to draw original graph, which is 3 to the power x graph, and then which is here, and then move 9.75 to the right. So the graph just moves 9.75 units to the right. So these are the two transformations that we covered: is vertical translation and horizontal translation. Um, so as a summary, f of x plus a moves the graph a units up. F of x minus a moves the graph a units down. F of x minus a in the bracket moves the graph a units to the right. F of x plus a moves the graph a units to the left. We're just going to replicate the same um, transformations using now another type of function. Maybe let's say take a quadratic. Let's say I'm taking x squared minus 2x as my function. So that becomes more evident and clear. How do we sketch the graph? So now, first thing is that let's say I'm moving the graph to the right. So if I take the value at 0, it's the same function. Now, as you can see that it moves to the right. If it is moving to the left, if a is negative. Now, for example, if it is x is negative 4, it is moved 4 units to the left. And if my f of x is outside here, a is outside, then it moves up or down. So if I play the slider now, you can clearly see it moves up and down. So this is the basic translation property. Now let's just go on to the other type, which is reflection. Reflection is actually pretty simple. When you look at the reflection part, there are two things that you're asked in the exams, that is negative x reflection and negative of x reflection. Now this is basically when you replace x with negative x, your graph basically gets reflected across y-axis, reflect in y. And when you make the entire function negative, it basically means that the graph reflected in x-axis. So it reflects in x-axis. Now, let's just have a quick look at the example. I have my function here. I'm just going to take, let's say, f of minus x here. So it can be clearly seen that the graph got reflected across y-axis. And if I got minus here, it gets reflected across x-axis. And now, if I take a function such as, let's say, 3 to the power x, our first function, now 3 to the power x. Now, when you talk about the reflection here, so y equals to 3 to the power x, actually, if I have f of minus x, it means that it is 3 to the power minus x. So when you're asked to sketch graph of 3 to the power minus x, it's actually a reflection of 3 to the power x graph across y-axis. Now, if you're asked to do negative of x, which means that you're asked negative 3 to the power x, it means that the graph gets reflected in x-axis. So it is something like here, and it cuts at the negative 1, and it goes down. So this is your f of minus x, and the second one that you see here, this is negative f of x. Now, if I look at some of the combined transformations that I'll probably make us more clearer now. For example, if I've been asked to calculate or sketch the graphs of, let's say, 3 to the power minus x minus 7. In this case, your graph is reflected in a y-axis. So you take reflect in y-axis. So you take 3 to the power x graph, reflect in y-axis, and then move 7 units down. So now when I look at this graph, if I reflect in y-axis, it's something like this. Okay, and I move 7 units down, it is going to be at y equals to minus 7 here somewhere, and it's going to cut the y-axis at minus 6. So the new graph that you get probably is going to be something like here, where you got the horizontal asymptote as minus 7. And of course, for these roots and all, you got to solve. Here, y-intercept, you plug x as 0, you get the y-intercept straight away. So that's how you do the basic reflections and transformations. Now, we're going to quickly touch base upon dilation. So dilation is basically its form of multiplying entire function by a constant, or the x values with a constant. So it is whether it is af of x or f of ax. Now, when it is af of x, it is your vertical stretch factor, Okay, factor or vertical dilation. If it is f of ax, then it is vertical stretch factor by a here, and if it is f of ax here, it is horizontal stretch factor or horizontal dilation by 1 over a. Now, in this case, it is very important that you remember that your y values get multiplied by a, and here in this case, your x value gets multiplied by 1 by a. So this is something which is interesting. Let's just like take some examples. Now, for example, here is my function. Now, if I make the function af of x as slider, if I have my function slider as af of x, you can see that when a is, let's say, 2, my y values got stretched by 2. So actually what's happening is that each x value, which were earlier at, let's say, uh, x is remaining same, but your y is getting double. So it was 1, now it became 2. If, for example, here there are any points close to 2, that will become close to 4. So each y value gets double when you are doing a vertical stretch. Now, similarly, I can show with some other function as well. So let's take some other function. Now, if I take a function such as x square minus 5, let's say x square minus 2x, I can clearly see that the vertical stretch factor, so this is 1 comma negative 1, this is 1 comma negative 2. So this is your vertical dilation. Now, when you talk about the horizontal dilation, now in that case, it is uh, f of ax. So now when you see f of ax, as I said that, if it is f of 2x, your y value remains same, but x value get multiplied by half. So y value is 2. Let's say here it is 2 comma 0. Now if I multiply only x value by half, so half times 2 comma 0. So now the same point comes at 1 0. So this is the point. Similarly, if there is any point as 4 comma something, it become like 2 comma something. If it is x coordinate, basically gets halved. And so f of ax, you just take the shortcut as horizontal stretch factor by 1 over a. So if it is f of x over 2, you're going to multiply each x value by 2, keeping the y same. So if I can show it to you here, if it is if the slider is at a at 0.5, so if I take a at 0.5 here, you can see that the x values got multiplied by 2. So this is how you do the basic transformations linked up with the functions. Now I'm going to take one example on exponential function, which covers almost all the properties. So let's say my function is negative 3 times 4 to the power x plus 7 is my first function. And second I'm going to take is y equals to 1 over 2 to the power x minus 2, and here is negative 3. So I have to sketch these graphs and state their properties, that what is actually happening to the graph. So let's take the first base graph, which is 3 times 4 to the power x. So here I am taking my base graph as 4 to the power x. Now, when you sketch base graph 4 to the power x, the graph looks like same thing as the one which you just sketched. So negative. So this is 4 to the power x. And now I'm going to talk about the transformations first, step by step. So this negative basically reflects the graph in x-axis. So you're going to first reflect the graph in x-axis. And that is nothing but negative 4 to the power x. So you can see that this is my reflection across x-axis. Then what does this 3 do? It vertically stretches by factor 3. So this point, which is you see at 0, minus 1, it actually will come somewhere here. So I'm just going to now multiply this same function by 3. So which is here 3 times negative 4 to the power x. You can see it's a vertical stretch factor. So reflect in x, vertical stretch factor 3, and then move 7 units up. So when I move 7 units up, you can see, or let's say here, if I add x plus 7, so you can see the graph moving up now. So the horizontal asymptote here is actually at y equals to 7. So in short, if I have the exponent of the form y equals to a, b to the power x plus c, assume that b to the power x is the base graph, a is the vertical stretch, and c is the vertical translation, which is also referred as y equals to c as the horizontal asymptote. So this is how you kind of do the basic transformations. Now let's just have a quick look at the second example that is we have taken. So our function is y equals to half to the power x times 3 and negative 2. So when you have half to the power x, I can rewrite this as half to the power x can be written as 2 to the power minus x. And so I can rewrite the function as negative 3 times 2 to the power minus x minus 2. So here, first I'm going to reflect the graph in x-axis. So let's take the function first, which is my basic function is, here is negative 2 to the power x. So I'm going to take 2 to the power x, then reflect in x-axis. So that's going to be minus 2 to the power x here. Then vertical stretch by 3. So 3 times the vertical stretch. 3 is the vertical stretch. Reflect across y-axis and move 2 units down. So that's here. The graph is here. So you can see that horizontal asymptote here is approximately y equals to negative 2. So this is how you do the basic graphing of the exponential function using the transformation skills. And I hope this was helpful.